Good morning, everybody. Welcome to chemistry. Today is, what is today? Wednesday, May 27th, 2020. We only have 11 days left of school. Hang in there, folks. Let's start today by going over to the agenda and taking a look at the plan for today. Nope, wrong one. Here we go. And okay, so yesterday you took your equilibrium quizam. I have not gotten a chance to grade those yet, but I'll get them graded as soon as we're done today and get your results right back to you. Mornings are just a little hectic in my house, so we'll get those back to you as soon as possible. And then if you have any questions, don't hesitate to shoot me an email, or you can ask me Friday during class, or I think Monday I'll do some office hours so you guys can come over and ask me if you have any questions. Hopefully today you got a chance to print some thermochemistry notes. We're going to do some guided notes together today. So if you go over to the Google Classroom, which is right over here, you'll see this uploaded. So I created a new, there we go. I created a new module or unit for us. And I put some things in there last night that go over for the next couple of days for you to do. This crash course in thermochemistry, this is what we're doing today. And then tonight I have this specific heat worksheet and the answer key there, and the thermochemical equations worksheet and answer key for you there. This worksheet is a really good review of some stoichiometry and combines your knowledge of stoichiometry with thermochemistry. So that's a good thing to work on. It'll kind of jog your memory on some stuff that we've done earlier this year. And you'll definitely want to keep those stoichiometry skills up. I got my roster for AP Chem next year, and I see a lot of your names on it. So I'm very excited to see that I get to have many of you as students again next year. So yeah, you want to keep those stoichiometry skills up for varsity chemistry. So we're going to do those guided notes today, and hopefully I'll have a chance at the end of the time together to do a quick example for the stoichiometry and on that practice worksheet. I got those 2 worksheets for you to practice tonight. And then tomorrow I'm going to have you guys watch a TED Ed video, fill out a Google form, and then there's a potential energy diagrams worksheet that I uploaded here. Just a review. You guys already know your potential energy diagrams, but I think that would be a nice little review of some recent units with you. We talked about it in kinetics. We talked about energy diagrams in equilibrium, and then it's coming up again. So it's kind of, again, coordinating all this knowledge that you have together. So you can take a look at that. It should probably be pretty quick and easy for you to do. And then I have a kitchen lab for you tomorrow. I'd like you to actually turn this in on Google Classroom. So you'll notice that I created this efficiency of a microwave kitchen lab is actually an assignment, and it's due by Friday at 9 a.m. when we meet again. Okay, so this is kind of a fun thing to do in your kitchen. You're basically going to, I'm assuming most of you have a microwave, okay? If you don't have a microwave, let me know. I know it's not easy to go over to a neighbor's house right now, but hopefully you have a microwave, and we're just gonna do a quick little lab where you test the efficiency of your microwave. One thing that's very important here is basically what you're gonna do is you're gonna get a microwave safe container and put some water inside of it. And you're going to put that water in the microwave. Just follow the instructions. It's pretty straightforward. But here's the very important part. In step 4, it says place the water and food in the center of the microwave. So what I mean by that is, if you look up here at the safety precautions, I'm going to go ahead and highlight this part because it's important. Okay, notice the safety precautions here. It says, don't place a thermometer in the microwave, number 1. And number 2, beware of something called superheating. So if you just take a bowl or microwave safe dish with some water and put it in the microwave, there's something that can happen called superheating, where if there's no place for bubbles to originate, and boil, sometimes that water will not look like it's boiling, but it's actually above boiling point. If you remember back to the demonstration I did for you, where it was the super saturated sodium acetate, where I put just a single crystal in there to get it to solidify, and that acted as a point of nucleation. We also talked about how clouds need particles of dust as a point of nucleation. We talked about how in a champagne glass, there's a small crack or an imperfection that where bubbles originate from. That's called a point of nucleation. Anyway, you need to add a point of nucleation to your dish so that the water can have a spot to boil from, okay? So find a small piece of food, a pea, a bean, a tiny grain of rice. Just put a small piece of food inside the water before you put it in the microwave so that it doesn't superheat. Because if you disregard that and you're waiting for your water to boil, and it may be way past the boiling point, and then you open up the microwave and open it up, and you could burn yourself, and I don't want that to happen, okay? So you're just gonna basically put it in the microwave until it starts to boil. And then when you see the water start to boil, then you're gonna stop and do some calculations, and you're gonna calculate the efficiency of your microwave, which is kind of fun. And just if you follow the instructions, it should be pretty self-explanatory. The only thing that sometimes throws people off is figuring out the manufacturer, the model, the theoretical power of your microwave. These are just things that can be looked up. So sometimes if you open up your microwave right on the inside of the door, right in the frame, you can find some information about the manufacturer and what model you have. If you can't identify, if you read in this paragraph, it tells you what to do. If you can't identify the power of your microwave, use the internet to find the information from the manufacturer. And basically, you should be able to find something comparable where you find the power of your microwave. And then once you get the power, you can determine what the theoretical power is, what your microwave says it is, and then your experimental power is what you calculate in part 2. And we'll see how efficient your microwave is. So this is something I actually want you to turn in on Google Classroom. Okay, that's your lab this week, is a kitchen lab. All right, so that's that. And then on Friday, we'll come back together. We're going to talk a little bit about freezing point depression. I'm going to give you some more notes. And then I have another worksheet for you. There's an optional thing for you to do over the weekend too. We would be doing this in class if we were together. We would be making ice cream. That's a fun lab that we do as part of our thermochemistry unit. And so since we can't make ice cream together in person, I figured I would give you guys the instructions on how to do it yourself, and you have a few days to get a hold of the ingredients you need. If you just click on this here, it tells you the instructions on how to make your own ice cream. And I'll tell you about that freezing point depression on Friday, so you'll understand the science behind it. These are the ingredients that you need. So if you want to order some from your Amazon, or where if someone's going to the grocery store, maybe you can ask them to fill in any missing ingredients. It's kind of fun to make ice cream. It's a good weekend activity. If you have younger siblings, that's a really fun thing to do too. And then there's some discussion questions here. You do not have to do these discussion questions, but if you want to think about the science behind ice cream making, you can do that, okay? There's also a video here that I uploaded, and this video is Ms. Allen actually going through the motions of making the ice cream. So if you want to see somebody do it as an example, you can also watch Ms. Allen do it. Okay, so there is that. That's the week, okay? And then again on Tuesday of next week, you guys will have a quizam on thermochemistry, and then we'll do acids and bases next week. And I'll give you a quizam the following week. I think what I'll do the following week, because it's finals week, is I'll give you a quizam on Monday on acids and bases. And then, or maybe I'll just give it over the weekend. I haven't quite decided what I'll do yet. But we'll give you a quizam on acids and bases based on what I teach you next week. And then once you get your score back, you can decide, do I want to do a final project or not? And if you want to do a final project, I'll give you that opportunity to boost your grade up to 2 levels. So you could move from a B- to a B+, or you could move from a B+ to an A, depending on how good of a job you do on your final project, okay? And the final project will be an explainer video, similar to what Mr. Anderson does. So if you guys are interested in that, I'll just have you fill out a Google form saying, yeah, I want to do an explainer video, or no, I'm going to keep my grade. I would venture to guess, just looking at my grade book, that most of you are probably just going to keep your grade, because the vast majority of you are doing quite well in the class, which is great. So anyway, and that's the way the rest of the year will work. Okay, so we're almost there. Hang in. So let's go ahead and begin today with molecule of the week, okay? My molecule of the week this week goes along with the fact that I'm inviting you to make ice cream. Oh, that's not it. That's not what I was looking for. Here, let's try this again. Stop share screen. This is what I want. Nope, it doesn't want to. That's not for us. Let's see what else is there. Let's try this one more time. I'm going to do share screen a different way. Here we go. Let's look at it this way. Okay. Carrageenan is your molecule of the week. And this is it comes from an Irish word called carrageen, which means little rock. This is a molecule that's derived from red seaweed. And they're very large, highly flexible polysaccharides. A polysaccharide is just multiple sugars that are linked together. So it's a carbohydrate, okay? And they curl up to form helices, kind of like DNA. And this gives them the ability to form a variety of different gels at room temperature. In the US, carrageenan is allowed under FDA regulations to add to food. It's considered safe and non-toxic, and it's basically a gelatin substitute. So I don't know if y'all knew this, but gelatin is not actually considered a vegetarian substance. It's used a lot in like gummy candies, or obviously in Jell-O and jelly beans and whatnot. Gelatin is made from the hooves of animals. And so many vegetarians refuse to eat gelatin. So this is considered a gelatin substitute because it can form gel, like a gelatinous texture at room temperature. It acts as a binder, and it's a thickening agent too. You might find it in diet sodas, beer, toothpaste, sauces, and ice cream. So you may have heard that ice cream is made from seaweed. It's because of this molecule, carrageenan. It's also found to cause some inflammation in epithelial cells. So what that means is, though all the cells that line your digestive tract are epithelial cells, they're the cells on the surface, right? And they found that carrageenan can actually cause inflammation in those cells. And so people with diseases like irritable bowel syndrome or any severe inflammatory bowel disease claim that eliminating carrageenan from their diet helps to improve their gastrointestinal health. So when the FDA is looking for, or not the FDA, when a drug company is looking for drugs to treat something like that, where you have some sort of syndrome like an irritable bowel syndrome or something that's caused by inflammation of the digestive tract, they need to induce that disease, if you will, in a model organism. So they actually use carrageenan as the molecule to induce the inflammation in a model organism, like lab animals, so that then they can give their drug and see if it works to reduce that inflammation. So it's used in scientific research to help find treatments for people that have inflammation problems in their digestive tract. It also may be effective to prevent HPV and cervical cancer, but you guys already have a vaccine for HPV. So most of you have probably already taken that. And so that's a little bit of a moot point. But anyway, there's a picture of the red seaweed that it comes from. And that's your molecule of the week. So you can think of that when next time you're eating ice cream or when you're making it this weekend. All right, today I wanted to start with a demonstration for you, and I was very bummed because I realized I gave all of my balloons, I stole a bunch of balloons from my classroom before we were locked out of the school, and then I realized that I had blown them all up for my kids' enjoyment, and I didn't save any for science. So I'm gonna have to find a video. I found a video online instead for you. So sorry about this, but if you have a balloons at home, you can impress your friends and family with this same thing. So there's a quick little Steve Spangler video I came across on YouTube today that I'm gonna share with you. And it's not too long, just a couple minutes, just to capture your attention. And by the end of the period today, I'm hoping that I will be able to explain to you the science behind why we observe what we observe. So I'm going to go ahead and let you watch this now.
All right, and you're going to put your safety glasses on as well. So give you little safety glasses that are there. So I know it's fine. I know it's okay. Self-esteem's important. Take that one. All right. All right. So here. Glasses. Okay. So now here, watch this. Ready? So I'm going to light your thing on fire. There you go. And you light this on fire. Okay, so now here's what's going to happen. What I want you to do is this. I want you to take the balloon, and I want you to hold it over the top and just slowly get down to it. How close do you think you can get before it'll pop?
Probably right on it.
Keep going, keep going, keep going, and you finally get nice. All right, so a little explosion right there, not so bad.
I thought that was gonna be a
And we
long
get
one.
yeah, not bad. All right, so
Studio crew running for their lives. This is a good
but
one.
now this makes it even more fun. So watch what you're going to do here. You remember you have to have your safety glasses.
Got 'em
for this.
on?
Have mom and dad kind of help out. You're going to fill this with water. So you fill the balloon first with water.
balloons.
Is that fun?
Well, I have a long
So now
history with
this
these.
is going to be a problem. Okay, so watch. Take the balloon now and blow it up. You learn the difference between blow and suck.
Clearly. Yep.
Okay, so this is very, very cool. So this one will be yours. Oh,
Okay,
if there wasn't a hole,
in
all
that
right.
one. Oh,
This one will be perfect
Oh,
right
okay.
here. Okay, see it inside. Okay, so now watch what
must
happens.
have been from another experiment. left
Please.
over.
All right. So now this is very cool. Watch what happens. The camera's going to get in real close. Watch this. We're going to get down lower and lower and
we blow
lower.
water?
And look at this.
You are kidding me.
No,
It
it'll
doesn't
just sit there.
explode?
It just sits there.
Well,
Now,
I don't
water-
understand that science.
Isn't that very, very cool?
These are latex,
Yeah.
aren't they?
Water is a great conductor of heat. So it really does a great job of pulling it all away. Isn't that fun? So it pulls all the heat away. And so now all that heat goes through this very, very thin little membrane that's here and starts to heat up the water. And as the
I
water
would
starts to
never
heat up,
have guessed
isn't that
that.
cool?
Not in a
So it just
million
kind of
years.
keeps on going.
Will it
keeps on
boil?
going. Well, if you got it long enough there, and so who has time
I'll
to do
be
that?
darned,
Try it.
yeah.
Just make sure that I'm not lying to you.
I
so
would
If I'm
just
lying, I'm dying,
I would
right?
be sure that
That's
that
true.
would
So you're
just
just nice and
explode
close.
it. So
Yeah.
it's the water that transfers the heat.
Yeah, and so it's just a great conductor.
Will you
and so
look
it
at
pulls
that?
away. Now put it off to the side. Like try to put put this onto the side here like this. So that will see that will make it explode. All right, just to prove. I'm sorry. You don't have to do another newscast, do you? No, I didn't. Think so. Well, I'm sorry then.
Okay, we're going to go ahead and stop it there. So pretty cool. That's a very easy trick for you to do if you have balloons. And all you need to do is just blow up a normal balloon regularly, put it over a candle, and it'll explode just like that. Why? Well, we know that if you increase the temperature of the gas molecules inside the balloon, they expand, and that's what pops the balloon. But for some reason, if you add a little bit of water in there, the balloon doesn't pop. And that's because the water starts absorbing that heat energy instead of the air molecules. We're going to talk more about that later on at the end of our session today, where I can hopefully help you explain the science behind what you saw. But that's a pretty fun one to impress your friends and family with. All right, let's go ahead and start the guided notes today. So if you would please pull out that crash course in thermochemistry. Maybe you printed it out, or maybe you just want to access it on Google Classroom and take notes. I don't know how you guys want to do it, whatever functions well for you. But I'm going to go ahead and pull those up right now, and we'll go through the guided notes together. That's not anymore. Where did they go? There. Okay, So a little bit, by the way, my maiden name is up here, Miss Spiteri. I never changed that. Whoops. That tells you how old this worksheet is. I use this. I've been married for almost 9 years now, so I've been using this one for a very long time. Anyway, so it's still me that made this worksheet. That's just my maiden name. So the overall concept in thermochemistry, firstly, let's just talk about what this prefix thermo means. Okay. Thermo is a prefix that means heat. Okay. And so we're really studying the chemistry of heat. You can probably think of a lot of different words that begin with thermo, right? Like thermometer or thermostat, right? A thermometer measures how much heat or how hot you are. A thermostat is something that measures the heat in your house, right? Decides when it's too hot or too cold, and you can set the thermostat to a certain temperature so that your home maintains a certain temperature. A thermos is something that you would keep hot or hot soups or hot chocolate in to help trap the heat inside, right? So anything with that prefix thermo has to do with heat, okay? And the overall concept is that of this unit is that energy is exchanged or transformed in all chemical reactions and physical changes. Okay, so we're going to look at some chemical reactions and some physical changes, and we're going to look how heat is transferred during those processes. Okay, so it says this is just some background information. Most of you guys should be able to answer these questions already, but and if I'm going too fast, please let me know. But I'm just going to kind of fly through here because we've talked a lot about this stuff already, but please stop me if you have questions. So the first question is, what are the two types of vaporization? So if you think back, vaporization is the process of going from a liquid to a gas. And so there's two types of vaporization. They were evaporation, boiling, right? Remember, evaporation only takes place at the surface, like your dog's water bowl on a hot summer day, versus boiling is the bubbles of gas that occur throughout the entire liquid. Okay, the lowest possible temperature in the universe is 0 Kelvin. That's what we call absolute zero. And in degrees Celsius, that would be negative 273 or negative 273.15 to be exact, degrees Celsius. And there's kind of a neat video I considered showing you guys this week. It's called The Quest for Absolute Zero. If you're interested in watching it, you can YouTube search it. It's a Nova video. It's a little less than an hour long. If you're looking for something that is intriguing and scientific, you can watch that video and learn about the quest for absolute zero. Is all about how scientists are trying to reach absolute zero, but they're not actually able to attain it. So it's kind of a neat one, but it's an hour long. I decided not to make you guys watch that whole thing, but you might be interested in it. What are some common units of heat and energy? So common units of heat and energy are, if you think back to my college professor story, right? Remember the joules, or it might be kilojoules. Right? Remember, kilojoules is kJ, right? Lowercase k, capital J. Joules would just be an uppercase J. Also, calories. Calories are a unit of heat energy. So when we're looking at our food and we're looking at how much energy is in our food, a calorie is telling you how much energy that food will provide for your body. The abbreviation of calories is cal, but there's also kilocalories. Okay, and kind of interesting, a kilocalorie is actually what is represented on, let's see if I can do this here, on the packages of your food. So if you look at the nutritional information on a package of food, like this is a no-cal bar. These are one of my favorite things to eat for breakfast. And they have 190 calories in them, okay? But notice if you look at the calories, it's actually a capital C. It's a capital C calories, not lowercase c calories. That means that it's actually a kilocalorie. So when you look at your food and you see those capital C's, actually all of our food foods are in capital C calories. Those are actually kilocalories, which is 1,000 calories, right? 1,000 lowercase c calories. The reason why we do this in the United States is because most people aren't familiar with the metric system, right? So if you go to Europe or to Australia and you look at where they use the metric system commonly, they're very familiar with this prefix kilo, right? And so they know that a kilo means 1,000, right? But here in the United States, we don't use the metric system. So if you put kilocalories on our packages, people aren't going to know what that is. The general public won't know what it is. So instead, they get around it by just making it a capital C calorie, and that's really a kilocalorie. So in reality, this bar has 190,000 calories in it, right? Because I'm talking, as a scientist, I'm talking calories are lowercase c calories. There's 190 kilocalories or 190,000 calories. So just a small something to keep in mind. And that's going to be important later on. We'll see this towards the end of our session today. All right, next we have what is kinetic energy? And if you guys remember, now I have kinetic energy. Now I have no kinetic energy. Now I have kinetic energy. Now I have no kinetic energy, right? Kinetic energy is energy due to motion of molecules. And the equation for kinetic energy is that kinetic energy is equal to 1/2 mass times velocity squared. Okay, so as long as something has mass and it's moving, it has speed, right? Remember, velocity and speed mean the same thing, right? Just there's a directional component to velocity. But anyway, as long as something has mass and it's moving, it has kinetic energy, okay? And that the faster it's moving, the more kinetic energy it has, okay? All right, so let's go on. Part 1 says temperature and heat. So the objective of this part is that you guys know how to describe temperature and heat flow in terms of the motion of molecules or atoms, okay? So I'm gonna clear everything out so that I can scroll down here a bit. We can do this together. So students know how to describe temperature and heat flow in terms of motions of molecules or atoms. So blank is a measure of the average kinetic energy of molecules in a sample of matter. You guys should know this one. Temperature, that's the definition of temperature, right? Temperature is a measure of the average kinetic energy of the molecules in a sample. So the hotter something is, the faster the molecules are moving. We know this already. Okay, that has to do with kinetics and why collisions happen more frequently at higher temperatures, right? Which molecules have more kinetic energy, the water in your pool or the water in your spa? This one should be pretty straightforward for you. The molecules in your spa have a greater kinetic energy. Why? Because they're hotter. The water in the spa is hotter, right? It's at a higher temperature, and so therefore it must have, the molecules must have kinetic energy. I always like to say, if you could shrink down to the size of a water molecule and you could ride around on a water molecule in your pool, you'd be moving, but it would be like riding It's a Small World, right? But if you could ride around on a water molecule in your jacuzzi, you'd be going super fast, like Space Mountain, right? All right, next part says define heat. Heat is energy, a type of energy that's transferred between objects with different temperatures. Different temperatures. Okay, and so think about, like, if I were to pick up my hot cup of coffee here, okay, it feels warm to me, and that's because that my hand and the coffee are different temperatures. And so heat is always transferred from the hotter substance to the colder substance. So when I pick up this hot coffee, I feel that it's hot because there's heat energy that's leaving the coffee and going to my hand, and it's warming up my hands. That's what I perceive as hot. On the other hand, when I pick up this is my water bottle. It's been in the refrigerator all night long and it's super duper cold. Yum. Anyway, okay. When I touch this, it feels cold, right? And that's because my hand and the water on the inside are two different temperatures, right? Now, here's the important thing to remember. There is no such thing as coldness. There is no such thing as coldness. This water is not transferring coldness to my hand. No, 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 no. Heat is the only energy that's transferred, right? So what's happening is my hand is hotter than the water. And so heat always leaves the hotter substance and goes to the colder substance. So heat is leaving my hand and it's going to the water. And it's the loss of heat from my hand that I perceive as coldness. Isn't that neat, right? There's no such thing as coldness. There's only loss of heat. So heat always travels from the hotter sample to the colder sample until the samples are at equal temperature. In other words, I could keep touching this until my hand and the water are at the same temperature, right? So again, there's no such thing as coldness. There's only loss of heat. So that's a pretty cool concept. Now this reminds me of when I was a little girl, because I remember my mom and I would bake cookies or a pie or a cake or something. And maybe it was, it was a cake. I remember Mom and I baked a cake once, and you can't ice your cake or put frosting on your cake until it's cool, right? And that's just a principle of baking. If you've ever made cupcakes or cake, you know that you have to wait patiently for the cake to cool before you put the frosting on. Otherwise, it just crumbles everywhere and doesn't work. So I remember when I was a kid, we made a cake, and I said to my mom, let's just take the cake, it's baked, let's put it in the refrigerator, and then the refrigerator will cool the cake down, and then we can frost it and eat it sooner. And she said, no, you can't do that. I said, why not? And she said, well, because the cake will heat up my refrigerator, and it'll, and I remember thinking that my mom was crazy. I was like, no, it's not going to heat up the refrigerator. The refrigerator is going to cool my cake, not the other way around. Well, once again, Mom was right. Right. There was no such thing as coldness. The refrigerator doesn't transfer coldness to the cake. No, the cake would transfer heat to the refrigerator, and it would warm everything else up inside, which is why Mom didn't want me to do that. But, when you're a kid, you don't think that way. So once again, Mom was correct. And so here it says, draw the direction of the heat flow between a warm apple pie and the refrigerator in the drawing. So definitely the warm apple pie is going to be hotter, so heat is going to flow away from the apple pie and into the refrigerator, okay? Next question says, true or false, you burn more calories while you're jogging at night. Believe it or not, the answer is true. And the reason for this is because at night, the air is colder. And so you lose more heat energy. You lose more heat energy to the air, and then your body has to work that much harder to keep the heat of your body high so that you can continue to power your muscles and all that good stuff. So you actually lose more heat energy. So you actually burn more calories if you work out in a colder environment. You would sweat more and probably lose more water weight if you were to do it in heat, but you would burn more calories in the cold because of thermochemistry. So it's kind of interesting. All right, so that's that. Let's go on to part 2, energy transfers. Again, if you have questions, stop me. Hopefully it's pretty straightforward so far. Okay, energy transfers. Objective here. So students know chemical processes can either release or absorb thermal energy. If it's releasing thermal energy, that's exothermic. We've already heard these terms before, so hopefully this is somewhat review. I was kind of front-loading your brains. Exo sounds like exit, so it's like heat is leaving the system. And then absorbing would mean endothermic. Endo kind of sounds like into, so that would mean heat is going into the system, okay? So when energy is a reactant, if energy is on the reactant side, that means heat is going in, and that's an endothermic reaction. And when energy is a product, that means it's coming out, and therefore the reaction is exothermic. Okay, so these reactions are endothermic. Note here, and we've already learned this, endothermic reactions have a positive value for their delta H. So we're going to get into that delta H a little bit more on Friday, but delta H stands for what's called enthalpy. And I just think of it as heat. Just think of the H as standing for heat. And the reactions are endothermic. They're positive delta H values, which means the products have more energy in their bonds than the reactants do. So if you can maybe visualize what that energy diagram looks like, and you're going to do more stuff with energy diagrams tomorrow. So that'll help refresh your memory there. But anyway, what I can do here is literally, if I wanted to add heat into this equation, I could add the heat onto the reactant side. So I could add 43.2 kilojoules on the reactant side to the nitrogen and the oxygen over here, and show that, I'm sorry, it's not kilojoules. I take that back. It's kilocalories. Sorry, I need to check my units before I do that next time. Let's see if I can move this. Oh, it looks a little bit. There you go. Okay, so I can literally add that 43.2 kilocalories to the left side of the equation because it's endothermic and positive. So I add it to the reactant side. Same thing here. Okay, I can add 2.4 kilocalories to the reactant side, okay, to combine with the hydrogen and iodine to form hydroiodic acid. So that's how we could represent an endothermic reaction. They can either give you a positive delta H value, or they might just write the energy on the appropriate side of the equation. The reactions are exothermic. Note if they're exothermic, the enthalpy or delta H value is negative, and that would mean that the energy would be on the product side. So I don't have a ton of space to do this. You could totally rewrite it underneath here, but I don't want to do that because it's really hard to do on a computer screen. So instead, I'll just kind of add it down here. On the product side, I could add 57.8 kilocalories. And you don't need to worry about the per mole part, okay? We'll talk more about what that means in AP chemistry, but it's per mole of the reaction the way it's written. So it's like per 1 mole of water, or per 1 mole of hydrogen, or per half of mole of oxygen. It's just based on the coefficients that are here. Okay, again, I could add this here, 68.3 kilocalories. Okay, so you would just add it to the product side. All right, so that's endothermic and exothermic reactions. Hopefully that makes sense. All right, let's go on to part 3, phase changes and thermodynamics. So the objective here is that you know that energy is released when a material condenses or freezes, and energy is absorbed when a material evaporates or melts. So it's kind of funny because most people don't think of that when something freezes. Like, actually, I'm going to take this off screen share for just a moment. If you think about the freezing process, where you take some liquid water and you put it in your freezer, people think of a freezing process as being endothermic because the substance is getting colder, but that's not actually the case. What you have to think of is that this water is what we call the system, and the freezer is the surroundings. And if you think for a moment, if you take room temperature water, right, and if I put this in the freezer, remember, heat always goes from what's warmer to what's colder, right? So when heat's going from what's warmer to what's colder, well, that water is going to be warmer than the freezer. So that means heat is going to be lost from the water and goes to the freezer until that water solidifies and turns into an ice cube, right? Okay, and so that was the process of going from liquid to solid, and it's exothermic. Why? Because heat was lost from the system. You're always talking about endothermic or exothermic with respect to the system. The system is the molecules. Okay, so a lot of people get that wrong because it seems counterintuitive. That freezing is actually an exothermic process. Why? Because you have to remove heat from the molecules in order to get them to turn into a solid, right? You got to take their energy away to slow them down so that they can become that solid that just vibrates in place. Okay, so let's go back to those notes. Where did they go? Here we go. All right, so the phase changes that are endothermic, where you have to put heat into the system, right? Things that are endothermic are going to result in a product with higher kinetic energy, right? It's like the warming process, anything where they're getting warmer. So endothermic processes would be melting, right? Why? Because the surroundings are going to transfer heat into the system to get the ice cube to warm up and melt, for example. Vaporization, right? If you think of boiling water on the stove, you have to put heat in from the stove to get it to boil, right? And sublimation would be the other one. Sublimation, remember, is going from the solid directly to the gaseous phase and skips over the liquid phase. So again, you go from a solid to a gas. Well, where did all that extra kinetic energy come from? Well, it had to be heat energy that was transferred into the system. So that's sublimation is endothermic. The phase changes that are exothermic are the other three, right? I just talked about how freezing is exothermic. Condensation is the process of going from a gas to a liquid. Well, how did we go from gas to liquid? What happened to all the kinetic energy in the gas? It must have exited the system. That's exothermic. And deposition is going from a gas to a solid, right? What happened to all that extra kinetic energy from the gas to the solid? Oh, it must have exited the system. You always have to have conservation of energy no matter what, right? And then number 3 says, why do beads of water collect on the sides of an aluminum soda can on a hot day? It's funny, I've got a little bit of condensation on my glass here. I don't know, if, on my water bottle here. I don't know if you can see that. This happens a lot on a soda can if you're at the beach or something too, on a hot day. And a lot of people think it's actually the water that's being released from the inside. No, that's not what's happening. Actually, I mean, this is a sealed container, right? So where is all that condensation coming from? Well, it's actually the water molecules in the air. So water molecules, there's water vapor in our atmosphere, right? There's lots of water molecules floating around. You just can't see them. They're too small and they're colorless. And so what happens is when these water molecules in the air come into contact with the colder soda or the colder water, they condense, right? They turn from the gaseous phase into the liquid phase. Why? Because heat is leaving this system of water vapor and it's going into that surroundings, which is the colder substance, right? Heat always goes from the hotter substance to the colder substance. And when the water vapor loses heat, it turns into a liquid, right? When it loses that heat energy, it turns into a liquid, and that's why it's condensing onto the side of our container. So that's pretty cool. So why do beads of water collect on the sides of an aluminum soda can on a hot day? We can say that water vapor from the atmosphere, that's correct, loses heat to the cold can and condenses the surface. Okay. So that's kind of cool, kind of a neat way you can also bring science in next time you're out celebrating on a hot day. Okay, so that's it. That's part 3, phase changes and a little bit of thermodynamics of endothermic and exothermic. We're going to talk about endothermic and exothermic more on Friday. Okay. All right, last bit here. Let's do specific heat, okay? Specific heat is probably one of my favorite things to talk about. I know I say that a lot, but this one's true. I like specific heat problems. The objective here is that students know how to solve problems involving heat flow and temperature changes using known values of specific heat. Okay, now specific heat is something that's called, that basically it's a measure of how much energy it takes to increase the temperature of 1 gram of substance by 1 degree Celsius. Well, I don't know how to do a degree sign, so I'm going to write it out. 1 degree Celsius or 1 Kelvin. Yep. A measure of how much energy it takes to increase the temperature of 1 gram of a substance by 1 degree Celsius or 1 Kelvin. I'll get to that explanation further in just a moment. The key equation for defining specific heat is this: lowercase q equals m times c times, and I can't make a triangle on here, but it's delta T, right? The change in temperature, okay? Now let's talk about what these are. So Q equals MC delta T. If I could write it actually here, let me write it this way instead, because it's kind of hard for me to do this here. So I'm going to stop sharing. I'm going to write this on my whiteboard instead. If I were to write this equation, if we were in person I had my whiteboard in the classroom in front of me, I would write it like this: Q equals MC delta T, okay? And to me, I often call this the Q equals MCAT equation because it looks like MCAT. I don't know if you guys know what the MCAT is. Many of you probably will take the MCAT at one of these days. The MCAT is a test that you have to take to get into medical school. And believe it or not, I did actually take the MCAT. I thought I wanted to be a doctor at one time, and I studied a really long time. By the way, the MCAT is a really tough test. It's like 8 hours long. You have to do writing. There's physics, there's biology, there's general chemistry, there's organic chemistry. It's a really tough test, and you don't get a calculator. Anyway, I passed the MCAT. I could have easily gone to med school with my score, but I just changed my mind and decided never to apply to med school. That's not the point. You have this 8-hour test that covers all these different topics, and you don't get any sort of equations, you don't get any sort of notes, they don't tell you anything. It's a tough, tough test. And so when it came to general chemistry and questions about specific heat, we knew that the equation that we used was the test we were taking, right? So we remembered it by saying, oh, it's the Q equals MCAT, because the MCAT is the test we're taking. So if you ever see me or hear me say Q equals MCAT, that's what I mean. It's just back from those days when I was a student and studying to go to med school. Anyway, so here's your important equation to solve these problems. And it's usually a pretty simple plug and chug style of problem, where the Q stands for heat energy, and it'll be in joules or calories, most of the time in joules or calories. The M stands for mass, which is in grams. The C stands for specific heat. I don't know why they chose C instead of S. I don't know, the S must be taken up by seconds, or entropy is S. I don't know. Anyway, the C stands for specific heat. And the units of specific heat are kind of funky. They're either joules per gram degrees Celsius. So gram and degrees Celsius are on the bottom. Or it could be joules per gram Kelvin. It doesn't matter whether your temperature is in Celsius or Kelvin, and I'll tell you why in just a moment. Okay. Or instead, if you have, your units are going to have to match. So if you have joules over here, then you're going to have specific heat in joules. If you have calories over here, then instead your specific heat that you'll use will be calories per gram degrees Celsius or calories per gram Kelvin. So you basically just choose the specific heat value that has the units that you need. Okay, we'll do some practice problems. And then delta T stands for change in temperature. And the change in temperature can either be degrees Celsius or Kelvin. It actually doesn't matter, right? Because the change is the same no matter which unit you use. In other words, if I go from 0 to 100 degrees Celsius, that's the same thing as going from 273 to 373 Kelvin, right? And so it doesn't matter which one you choose. Either way, the temperature change is the same. It's 100 degrees Celsius or 100 Kelvin, right? So the value of that number is the same. It doesn't matter what unit you have, Celsius or Kelvin. It's the same, okay? All right, so let's do a couple of practice problems or let's learn a little bit more about specific heat here. And then we'll get out of here today. Okay, so here's a good question. It says, imagine yourself at the beach on a warm summer day. I know, have you guys been to the beach lately? It's so nice. Feels like I felt like I refilled my soul to go to the beach. I almost felt like I was on vacation, right? Anyway, you go to the beach on a hot summer day, you kick off your flip-flops when you get to the sand. And I don't know about you, but when I get to the sand, it's like, ow, 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 right? It's hot, 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 hot. And then you get over to the water and it's nice and cool, which is kind of weird if you think about it, because both the sand and the water are being exposed to the same heat source, the sun, right? So why is it that the sand heats up so much and the water doesn't, right? And the reason why has to do with specific heat. It takes a lot more energy to heat up the water than it does the sand. So let's go ahead and just put that into words here. The water has a higher specific heat than the sand. In other words, what that means is it takes more energy to heat up water. Remember, the definition of specific heat is how much energy it takes to increase the temperature of 1 gram of a substance by 1 degree Celsius or 1 Kelvin, right? So how much energy does it take to think about 1 gram of water? How much energy does it take to increase the temperature of that by 1 degree Celsius? Well, think about what it means to increase temperature, right? If you want to increase temperature, think about when you guys did that kitchen lab. Remember when we had the heating curve and I made you guys like melt ice and boil and water and measure the temperature every 30 seconds? Right? And as that temperature increases, in order to increase the temperature, I have to increase the kinetic energy of those molecules, right? So in order to increase their kinetic energy, I have to break apart the bonds that are holding them together, right? Those intermolecular forces. So for this reason, I'm going to ask you this, and I hope you know the answer right off the bat. Water has a really, really high specific heat compared to other substance. In other words, it takes a lot of energy to heat up water compared to other substances. Why do you think that is? Correct, it's hydrogen bonds, right? I told you, if you ever get a question about water and you don't know the answer, just say because of hydrogen bonds and you're probably right. Water has hydrogen bonds, so it takes a lot more energy to break apart those strong hydrogen bonds and get the molecules moving faster and have a higher kinetic energy, right? And so, it takes more energy to heat up water, and therefore the water is cooler than the sand, right? Sand warms up faster. I'll tell you guys a quick story too. When I was 30 years old, I moved back in with my mother. I know 30-year-old ever plans to move back in with their mother, but I did, okay? And actually she became my best friend. I adore my mother. But anyway, my mom has a pool in the backyard and she has a jacuzzi too. And there was one night that I wanted to go sit in the jacuzzi, and I didn't know how to turn on the heater. I don't know how to do that. But my brother used to be a pool guy. So I called him up and I said, and my brother was a pool man during his summer vacations from college. So I called him up and said, hey, can you walk me through this over the phone? Tell me how to turn on the jacuzzi. And so he did. He, walked me through it. I turned on the jacuzzi, sat in the hot tub all night, and everything was great. Yeah. About 2 weeks later, I was walking around the backyard and I was talking on the phone, and I just dipped my toe in the pool, how you kind of do when you're just chatting, and yeah, I don't know. Anyway, I dipped my foot in the pool, and the pool is hot. It's warm. And I realized that when I was back there fooling with all the valves, I accidentally turned on the heater for the pool. And it had been heating for about 2 weeks, right? I kid you not, I'm a chemistry teacher, right? So the first thing I look at is I look at the pool and I think, holy crap, that's a lot of water. And water has a high specific heat, right? Which means it takes a lot of energy to heat up that water in the pool, which means my mother's electricity bill that month was sky high. She was so mad at me. It was hundreds and hundreds of dollars. She was so mad at me. If she could have grounded me and kicked me out of her house, she would have. Of course, she didn't do that. But anyway, I repaid her by taking her on a trip to Africa. Pretty good trade, right? But anyway, my point being is that water has a really high specific heat. It takes a lot of energy to heat up water in a pool. So if you ever are around a heated pool, appreciate it, because it takes a lot of energy to do that. Another great example of this is just making spaghetti on the stove, right? You put spaghetti in a pot, a metal pot, and you start heating it over the same heat source, the stove, right? And think about which one heats up faster. Is it the pot or the water inside? Well, I mean, obviously, most of you probably know that if you touch the pot, you could burn yourself. But if you touch the water inside, it's still pretty cool to the touch. The pot heats up a lot faster. Why? Because it's easier to change the temperature of metal than it is to change the temperature of the water, because water has a really high specific heat. In other words, it takes a lot of energy to heat up water molecules. Okay. And so hopefully that's starting to make a little sense. So let's look at the last page here. It says important hints to know. Each substance has a unique specific heat value that can be measured without changing its identity. There's some labs that we would do. Gosh darn it, if we were in lab right now, I could have you actually measuring specific heats of unknown metals, and then I could give you a list of specific heats, and then you should be able to actually identify the metal based on the specific heat that you've determined experimentally. So that's pretty cool, which means you can use specific heat to identify a substance, and that makes it a physical property, right? Just like density or melting point or boiling point, specific heat is a physical property that can be used to identify a substance. Okay, doesn't matter, gold always has a certain specific heat. You can look it up, right? Silver has a certain specific heat. Water has a certain specific heat. And that specific heat of water is 4.18 joules per gram degree Celsius. And I'm just going to put here, I'll do this. That little star is my degree sign, okay? Or it's actually in calories, 1 calorie per gram degree Celsius, or you could call it per gram Kelvin. It means the same thing, okay? So actually, this is interesting. So here's the conversion between joules and calories. 1 calorie is equivalent to 4.18 joules. But this is kind of interesting. This is the definition of where a calorie comes from. We use calories all the time, often most of us every day, to look at calories in our food. Well, the definition of a calorie is how much energy it takes to increase the temperature of 1 gram of water by 1 degree Celsius. In other words, the definition of a calorie is based on the specific heat of water. If I have 1 gram of water, which is 1 milliliter of water, just think about how tiny that is if you think back to the graduated cylinders, right? 1 little milliliter of water the amount of energy it takes to increase the temperature of that water by 1 degree Celsius is a calorie. And that's where the definition of a calorie came from, okay? All right, so let's do one quick example here. I'm gonna do one example of this. I'm gonna let you guys try the other two on your own. And then I'll give you the answers to them. And then I just wanna do a quick example of that stoichiometry one. And we'll be out of here, okay? So this is determine the quantity of heat required to convert 10 grams of ice at 0 degrees Celsius to vapor at 100 degrees Celsius. So I'm just gonna use my Q equals MCAT equation. I wanna know what's the Q equal, oh, that's not Q equals, the mass is 10 grams, right? The specific heat, we're talking about ice or water. And I can figure this out in calories or joules. I'll just plug in calories because it's easier to plug in a 1. It doesn't say whether they want the answer in joules or calories. And then the change in temperature is just 100 degrees Celsius. Okay? And so the Q is equal to 1,000. It takes 1,000 calories to increase the temperature of 10 grams of water from 0 to 100. That's it. Or we could say that it's 4,180 joules. You could just use that conversion factor to do that. Obviously, I think this one, the calories is a little bit better simply because it's the proper number of sig figs, right? You should only really have 1 sig fig because of the values given in your problem here. So I would choose that one, but either one is fine. These problems weren't actually written for sig figs when I wrote them 9 or 10 years ago. I didn't actually teach sig figs. I know. You guys probably wish you had me as a student back then, but you'll thank me one day that you know your sig figs so well. Okay, let me just give you the answers to these other two, and you guys can try them on your own. Question number 2, the answer is, is 1,250 degrees Celsius. And question number 3, and again, these might not be the proper number of sig figs. As a matter of fact, they probably aren't. So don't stress about sig figs for these. This one should be 135 joules. Okay. And then notice I have to give you the specific heat of iron here. Okay. So you guys have a lot more practice on specific heat tonight. There's a worksheet for you to do. Answer keys are all there. The only thing I wanted to do with you before we leave today is to just go over, well, that's it for that. Let's see. I just wanted to go over, not that. Nope, not that. Oh, there it went. Here, go back here. This thermochemical equations worksheet, I just want to do one example with you guys because there's some stoichiometry on there. Okay. Or maybe I could just pull it up and, oh no. Oh, there it goes. Okay. So I just want to show you kind of what I did here with these because I mean, all my work is here, so you should be able to follow it pretty well. But it says here, what is the heat change when 6.44 grams of sulfur reacts with excess oxygen according to the following equation? So it's a little bit of limiting reactants, excess reactants. So we need to first convert to moles because these units here, even though it just says kilojoules, you can think of it as kilojoules for every 2 moles of sulfur and 3 moles of oxygen and 2 moles of sulfur trioxide. So first thing you have to do is convert from grams to moles of sulfur, which you guys should be able to do, right? You always, when in doubt, always start by converting to moles. So we're going to convert to moles of sulfur first, but then what this actually means is that it's an exothermic reaction and that 791.4 kilojoules of energy is released for every 2 moles of sulfur. Look at the coefficients in the equation. So it's for every 2 moles of sulfur, for every 3 moles of oxygen to form 2 moles of sulfur trioxide. So notice I had to put this 2 in front right? Because I'm getting negative 791.4 kilojoules of energy for every 2 moles of sulfur. In other words, this 2 moles has to match that there, right? Okay. And then down here, you'll see I've got 4.72 grams of carbon, and we converted from grams to moles. And then I can keep the 1 mole of carbon here. Let's do this. 1 mole of carbon here, because the coefficient of carbon is 1. Okay, so just notice that the kilojoules and the moles, this number down here will match the coefficient here because it's the kilojoules of energy as this reaction is written. Okay, so hopefully that makes sense to you. If you have questions, don't hesitate to shoot me an email. Okay, and that's it. I'm going to stop today because I know that I've gone over our time already. So I'm going to go ahead and pause recording, stop recording.